All right, let's jump right in. We're going to talk about something that sounds like it just shouldn't exist. Random matrix theory. I mean, seriously, it's a whole field of math that's found this incredible, shocking amount of order and, predictability, but it found it hiding in the one place you would never, ever think to look. Just pure, absolute chaos.
So let's really get into this, because at its heart is a huge mystery. How is it even possible that one single mathematical idea can be like a hidden blueprint that connects all these wildly different parts of our world?
No, really, think about that for a second. We're talking about the energy levels inside an atomic nucleus, the stability of these giant, massive supercomputer calculations, the ups and downs of the stock market, and even the way prime numbers are spread out. I mean, what on earth could those things possibly have in common?
So what you're looking at here is this absolutely stunning pattern. These core mathematical structures, right? They're called ensembles, and they pop up again and again all over the place in completely different fields. You've got a physicist over here calling something a Gaussian ensemble, and then a statistician over there is calling it a normal distribution. But get this, they're talking about the exact same underlying mathematical DNA. That's not a coincidence. No way. That's a massive clue that something really fundamental is going on here.
And the answer to that clue, it's the random matrix. Yep, just a simple grid of numbers where every single number is picked completely at random. This is the hero of our story today.
Okay, but to really get why this is such a big deal, we first have to tackle a huge myth about what randomness even is. Because it turns out our intuition, it's usually just completely wrong.
You know the feeling, right? We just instinctively assume that if you, say, fill up a giant spreadsheet with totally random numbers, the result is just going to be a chaotic, patternless mess, a jumble. And the bigger you make that spreadsheet, the messier and more unpredictable it should get, right?
Well, what if that's not just wrong? What if it's the exact opposite of what actually happens? And hey, don't feel bad if that's what you thought. Even one of the greatest minds of the entire 20th century got this one totally wrong.
So back in 1947, you have the absolute genius John von Neumann. He's thinking about how stable big calculations are, and he comes up with this, a rule of thumb for a really key property called the condition number. And he figured pretty reasonably that for a matrix of size n, its condition number should be somewhere around n.
But the mathematical reality is just mind-blowingly different. This shows you just how bizarre these things are. Von Neumann's intuition wasn't just a little off. It was off by, well, infinity. The actual expected value is infinite. The probability of the condition number being small is basically zero. And this tells us something huge. Random matrices aren't chaotic at all. They're actually bizarrely and rigidly structured.
So here's the key takeaway, the incredible irony of it all. The more randomness you throw in, by making the matrix bigger and bigger, the less random and the more predictable its properties actually become. It's completely counterintuitive.
So what does this hidden structure actually look like? How does it show up? Well, it's time to see this order emerge right before our eyes. And trust me on this, it is absolutely beautiful.
Okay, so what we're looking at here is a plot of a matrix's eigenvalues. You can just think of them as its most important characteristic numbers. Now, for a small random matrix, look, it's a mess. It's jagged, chaotic, pretty much exactly what we'd expect. But watch what happens as we make the matrix bigger and bigger. Look at that. The more random numbers we cram in there, the more that randomness itself forces the eigenvalues into this stunningly perfect shape, a perfect semicircle. Incredible.
And that's not some fluke, not a one-off. It's a fundamental law of mathematics. It's called Wigner's semicircle law. And a really good way to think about it is it's the matrix version of the famous central limit theorem. The one with the bell curve? This is the same idea, but for matrices. It's a universal law for randomness on a massive scale.
And look, this deep predictability, it's not just some cool theoretical party trick. Oh no. Understanding this hidden structure, it unlocks the power to solve problems that would otherwise be completely, totally impossible. Let's check out one of the most incredible examples of this in action. This is going to blow your mind. So imagine you go to a computer scientist and you give them a challenge. Find the largest eigenvalue of a random matrix that has 1 billion rows and 1 billion columns. I mean, just trying to do that the straightforward way, it would take more computer memory than exists on every supercomputer on the planet combined. It is, for all practical purposes, impossible.
But by using what we know from random matrix theory, we can pull off what feels like an incredible magic trick. So the first big insight is that you can swap out that impossibly huge, dense matrix with a much, much simpler one that's mostly empty space. But it has the exact same properties that we care about. And then comes the real shortcut. It turns out the answer we're looking for, that largest eigenvalue, is basically determined by just a tiny little corner of this new, simpler model.
And the result, a problem on a scale that is just staggering, a problem that should be totally impossible, becomes solvable. Not just solvable, but solvable in seconds. On a regular laptop, that is the power you get when you find the hidden structure in chaos.
But the story doesn't end there. It gets even deeper, even weirder. Because these universal patterns we're seeing in random matrices, they don't just solve practical problems. They point towards one of the deepest, most profound mysteries in all of mathematics. See, this amazing structure we've been looking at, this predictable pattern in the eigenvalues, it doesn't just show up in physics and engineering. It appears somewhere else, somewhere it just has absolutely no business being. Okay, just take a look at these two graphs. I want you to really look at them. They are, for all intents and purposes, identical. The graph on the left, that's the pattern we've been talking about all this time. It's the spacing between eigenvalues in a random matrix. It also happens to describe the energy levels in a heavy atomic nucleus. Now, the graph on the right, that shows the spacing between the zeros of the Riemann zeta function, the super mysterious fundamental thing in pure math that basically holds all the secrets to how prime numbers work. So, why are they the same? Why does a pattern that's born from pure, unadulterated randomness perfectly match a pattern that seems to encode the deepest structure of our number system? The honest answer? Nobody has a clue. It is one of the most profound, completely unexplained connections at the very heart of mathematics. And so that leaves us with this incredible, tantalizing question to ponder. If the hidden rules of pure randomness are exactly the same as the hidden rules of prime numbers, what does that tell us about the fundamental order of the universe itself? What other deep secrets are just hiding there, right in plain sight, just waiting for us to find them?